Okay, so we're moving on to 15.5 now, which is a relatively short section. We're only going to look at a couple of examples here. The topic is surface area. And if you recall in Calculus 2, we do cover surface area specifically for surfaces of revolution. So where you have a curve in the xy plane and you rotate that curve around an axis, creating a surface. In Calculus 2, we develop a surface area formula for the area of that surface. And that's great, but it's restrictive because many surfaces that we care about can't be thought of as surfaces of revolution. So we need something a little bit more general. How do we find the area of kind of a more general surface where the surface is given as the graph as a function of the form f of xy? So to develop this idea, here's an example or a diagram of a surface S, which would have been graphed, is a piece of the graph of the function f of xy, which is not showing up here, but we're just going to refer to it as f of xy. The goal is to determine initially the area of a piece of this surface that lies directly above this rectangle Rij. Okay, so we're just going to start with a single rectangle. Now, the way we're going to do this, as we've been doing anytime we develop an application of an integral or a double integral, is we try to create a Riemann sum somehow. And remember, Riemann sums start out as approximations for something, and then we apply a limit to that approximation, which makes the approximation accurate. So we're going to try to approximate the area of the surface over this rectangle Rij before trying to get an accurate answer. And the way we're going to do that is we're going to select the point here in the xy plane on the in the rectangle Rij that's closest to the origin. And this is just because it makes the work simpler. We can derive a similar, or we could derive the surface area formula in a different way, but this will make the calculations that we do a lot easier. So that's going to be this corner of the box, or sorry, of the rectangle here, closest to the origin. Okay. If we were to plug that point into our function, f of xy, it's going to take us to this point here, Pij. The way that we're going to approximate the area of this surface here is we're going to first determine what the tangent plane to that surface is at Pij. We talk about how to find equations for tangent lines in chapter 14. And then what we're going to do is use the area of that tangent plane that lies directly above this rectangle and treat that as an approximation to the true area of the surface S above that rectangle. And you can kind of see from this picture, if this rectangle Rij is small enough, the rectangles, or the piece of the tangent plane up here appears to be a decent enough approximation for that little area. So let's go back to how we find the equation of a tangent plane. If we're looking for the equation of a tangent plane at the point xi, yj, which is what we're labeling this point right here, xi, yj, I wrote my notation a little bit different from how we see it in chapter 14. So ignore the delta z for a second. Z minus z naught is what you're used to seeing here. But remember, z naught is really the same thing as f of xi, yj. It's the z coordinate of this point right here. Is equal to the partial of x evaluated at that point times x minus xi plus fy, the partial with respect to y at xi, yj times y minus yj. And now what I want to do is think of x minus x, or sorry, I said x, I meant to say z. Think of z minus z naught, or z minus y, xi, yj as a change in z. That's a reasonable interpretation of that. So I'm going to call this delta z. Our goal here is to determine how to find the area of this little piece of our tangent plane up here. Now, before I go any further, we should mention that this tangent plane and this little piece of the tangent plane that lies above this rectangle is not necessarily a rectangle in its own right. It looks like one. but in general it's not. What it is, however, is a parallelogram. And the way we can sort of make sense of that is if you take this point on the little rectangle down here, and then you use this point here to create a vector where xi, yj is the initial point of that vector, and this corner right here would be the terminal point. And then create another vector going along this edge of this subrectangle, or I'm calling it a subrectangle, which it will eventually be one, but right now it's just a rectangle. Initial point here, terminal point here, creating these two vectors pointing away from that point. Those would correspond to the two vectors along the edges of this piece up here. And even though because this is a rectangle, these two vectors will have a right angle between them, but there's no reason that the two vectors up here have to have that same right angle, and in general they won't. However, we know that two vectors that share an initial point always determine a parallelogram. So really what we're looking for is the area of a parallelogram here. And in chapter 12 we talk about a formula for doing that if you have the two vectors that determine that parallelogram. We're going to get to that point down here, but just as a reminder, if you want to find the area of a parallelogram, what we want is the absolute the magnitude of A cross B, where those are the two vectors determining that parallelogram. But we have to get to that point. So in order to do that, I need to know initial point and terminal point. I need to know how I'm supposed to come up with component forms for these vectors so that I can use them in a cross product. And the way I'm going to do that is I'm going to use the fact that we have this expression for, this equation for our tangent plane. And I'm going to think of this as delta z. And the points here and here that I'm using as my terminal point, you'll notice on the x and y axis, we're looking at our change from this point to this point as delta x. That would mean that this point right here has a representation of xi, which is this x coordinate, plus delta x, which takes me to this x coordinate. The y coordinate of this point is still yj because we're moving perpendicularly from or in a direction that's perpendicular to our y-axis, so there is no change in y going from this point to this point. That means that's my terminal point right there. If I want to determine what the change in z is in my tangent plane up here, then what I need to do is plug this point in to the equation of my tangent plane. So if you imagine doing that, first of all, the yj, when I plug it in here for y, takes this whole thing to 0. And then if I plug in xi plus delta x in for the x here, you'll see the delta i's the xi's cancel each other out, and the delta x is all that's left. And so what I'm left with is delta z equals fx xi yj times delta x. That's this right here. Okay, so this will be the change in z for this vector once it's mapped up here to my tangent plane, or that piece of my tangent plane. Similarly, if I use the point xi yj plus delta y, which would correspond to this point down here, plug it into the equation of my tangent plane, the change in z that I get from this point to this point is going to be given by this expression right here. So the partial derivatives times the change in either x or y are how I get the k components. That's the change in z, k components for those two vectors. So now going down to here, my vector a, which is you can see it right here. This is the same rectangle, same parallelogram that we see up here. Just kind of zoomed in a little bit. If I refer to this vector up here as vector a, we know already that the change in x from this point to this point is delta x, so that makes the I component for that vector. There is no change in y because we're not moving in a direction that would cause a change in y, so that's why you don't see a j component here. And then based on our discussion that we just did up above, the k component would be the partial derivative of x evaluated at this point xi yj times delta x. Similarly for vector b, there's no change in my x from this point to this point, but there is a change of delta y in my j component, and then my k component is going to look similar. So that gives me two vectors that determine this parallelogram here. If I want to find the area of that parallelogram, then what I need is the magnitude of the cross product of those two vectors. So here I've set up my cross product, and you can see here in these steps, this is what happens after evaluating that cross product. You know how to do cross products with 3x3 determinants, so I'll let you kind of make sense of the steps here. But I do want to point something out going from this step to this step. Delta x times delta y is this delta x times this delta y. That's going to correspond to the area of the rectangle in the xy plane that this parallelogram lies above. So what happened is, because it shows up in each of these terms, it's factored out, and we just call it delta A, which again, remember, corresponds to the area of that little rectangle. And this is what's left after doing that. So the next thing that we need to do is, first of all, note that this would be the vector A cross B. And one thing that's missing here that I'm going to write in is the magnitude of A cross B. Remember, the magnitude is going to be the square root of the sum of the squares of each of these components here. So if I square this, I'm going to get fx xi yj squared plus fy xi yj squared. And then the k component of this vector is 1. That's the coefficient there. So plus 1 squared, which is just 1. This would represent the area of that parallelogram for whatever point shows up here, xi, yj. Okay? So now the goal, if we go back to the original problem, is to find the area of an entire surface. So as we've been doing with double integrals up until this point, what we want to do is not use a single rectangle down here, but create a much larger rectangle, which we then partition into a bunch of sub-rectangles by partitioning our interval on our x-axis and our y-axis individually. And then what we would do is repeat this process for each one of those sub-intervals. So what that means is, if I'm calling the area of this parallelogram delta Tij, then I'm going to get a whole bunch of these. The way I like to think of it is kind of like shingles. If you think of the surface here as kind of a curved roof or something like that, then we're going to have a whole bunch of these little parallelograms kind of acting like shingles on that roof. And the total area of those shingles is going to be a decent approximation for the area of the surface itself. So if you can picture doing that, what we would want to do is add up the area of all of those parallelograms, all of those delta Tij's that we would produce up there. Notice that would be a double sum, and this area, we came up with a formula for that right here. So that's why this delta Tij turns into this formula right here. And then, I'm realizing I forgot to put my delta A there, so let me make sure I include that. That was part of that formula. Delta A is in there. Okay? So if we add all of those up, this again has the form of a double Riemann sum. You can see the xi, yj is the point that was selected in the sub-rectangle here. The delta A is present. That needs to be there because it's going to turn into a dA. This whole thing, and once I apply that limit, turns into this formula for the surface area of S. So it's the double integral over the region D, whatever we divide it up into those sub-rectangles, of the sum of the squares of my partial derivatives plus 1 under that square root. If I want to simplify the notation a little bit, or just use different notation, Leibniz notation in particular, my partial derivatives can be represented this way as well. So both of these are the same formula, just with different notation. We're going to wrap this video up here and do a couple of examples in the next video or two. But before that, I do want to point out that this formula may look somewhat familiar to you. Back in Calculus 2, we developed an arc length formula. this looks very, very similar to that arc length formula, and it's not a coincidence that it does. I'm going to let you sort of ponder over that on your own, but it's worth, if you don't remember the arc length formula from, I want to say it's chapter 8 in your book, you might flip back and look at that just for comparison. Okay?